Okay, I think I'm recording here, and this is Andy Reed, and this is for Unit 4, and this is how I can show a student-centered classroom where students are learning and doing. They're using information, they're not just memorizing information, and I am the facilitator of the lesson, and I'm definitely not just standing there and lecturing. So I'm going to go through kind of what I did for the unit and for the week, and then what I'm going to be doing next week and how it's all tied together. And it sort of will give a snapshot of my classroom and see how I'm implementing these ideas into my classroom and not just lecturing to the students and having them do worksheets or workbooks or 20th century stuff. They're doing things that are 21st century. So I want to talk about Bloom's taxonomy because that's a big part of it. A big part of the 21st century classroom is getting to these application, analysis, synthesis, and evaluation. So hopefully I can go to this slide several times and sort of talk about what I'm doing and how it relates to Bloom's taxonomy as well. The first thing I wanted to talk about is the basic setup of my classroom really quickly. I do half the students independently working, and then the other half of the students are with me, and then I'll be doing the lab with them, and they'll be working independently, but it's not just doing vocab or just doing book work. It is some of that, so that way I'm not reading the book to them, but they're reading it on their own. So basically, what they did this week was they worked with this simulator, which I really like this technology. I'll go ahead and click some of these bars. And we've been learning about speed and acceleration, but what we haven't learned yet about is force and mass. So it was a discovery learning thing where I wanted them to see what they could come up with as far as how is the mass and the force related to speed and acceleration. So they can push here on this little block here. They can add things to the block. They can see that it slows down. They can turn the friction off. And then do an applied force. And then one thing that's cool is if there's zero friction, as soon as you let go, the thing keeps moving and it stays at a constant speed. So this would be good for when I talk about inertia, which will tie in to what they're doing for their lab. And that is the idea that if something is in motion, it wants to stay in motion, and then if something is at rest, it wants to stay at rest. The other thing that the students were able to see is that you can have an acceleration in the opposite way, and yet the speed is still moving in this direction, this way, even though the force is the opposite way that the thing is moving, up until the thing actually stops. And it does show that speed is always positive, but the acceleration can be negative. So with that, it was an open-ended thing where they needed to write about what they learned, and slide this here real quick. Am I still recording? I'm sorry about that. Delay there. So their basic, this was their assignment here at the top. Read pages 22 to 25, answer the question, and then go to the simulator, and then write 2 paragraphs about what they learned about force, friction, mass, and acceleration, and they needed to include specific examples from the simulator, so I could tell that they were using the simulator in order to do the discovery learning. So this is one example Liam wrote. I noticed that in net force, even in the team's total mass, and that was one of the other ones that was similar to this one, but a little bit different. But in any case, the team's total mass is lost for the second and then regained as long as the other team was still pull with greater speed to help them win. Also in acceleration was a lot higher in the gauge when the object came to a complete stop rather than when the object first took off. In friction and regular motion, weight greatly affected speed and movement. So that was the key that I needed them to get from the simulator, was that the lower the weight, the faster you could push the thing. And that'll be really good for when we go over force equals mass times acceleration. And they'll have that discovery piece where they were learning and doing, and not just reading out of a book or listening to me talk about it. And it was student-centered because they really had to discover the learning for themselves. And I just kind of walk around the room as the facilitator. Students ask questions about it, and sometimes I'll give them suggestions. Hey, why don't you try this? Why don't you try turning the friction off? What if you add more weight to it, or less weight, or what have you? And I just sort of give them suggestions, but I don't go right in and tell them exactly what the learning goal is, or not what the learning goal is, but what the learning outcome should be. Another example, Cheyenne here, where to change acceleration, you have to apply a force or a friction force. Friction is always acting in the opposite way of the force, which is really hard to tell just from reading out of a book. But when you can see it in the simulator, that idea that friction is acting in the opposite way is a really good thing for them to pick up on their own. So overall I was really happy with the responses, and so that's the independent piece of the lesson. And then the other part, when they're with me, they are working on the project. So to start off, all the students had to do was, okay, I can replay this. Let me pause this. Okay, sorry about that. I had to pause it to let the videos load. But these are the toy cars that they'll be using for the discovery learning, to learn about kinetic energy and potential energy, and also to learn about acceleration, because the cars accelerate as the motor winds up and then you let it go. And then they'll be learning about speed. And for this particular one, this particular video, they were just learning about how to calculate the average speed of something. So I wanted to get them familiar with working, being out of their seats, and working with the cars and understanding that before I move to the more advanced lab, which I'm going to start next week actually, but I started with a certain group of kids. So this is just a quick video and just shows the students measuring the distance, and then they write down the time there. And what I would have them do is also I'd have them recording. So they would record it in slow motion so they could really tell right when it hit, and then they could divide by 4, because we talked about how it's exactly 4 times slower in slow motion, and just an added math piece to it. So that was just an example of something that we've already been working on. For this video, I broke apart 2 of those toy cars, and I actually put 2 motors, so both wheel axles have the motors, and then I took the metal piece off, the red part, so this one weighs less and has twice as much power. So the kids are really interested to see what this one could do, so we let it go in class, and then I'll sit back and watch. You know, it went really quick compared to the other cars, so they were pretty impressed by that. So what I plan on doing next week is this activity here, where the students are going to try to push the wooden block to overcome the inertia. So I really want to have them understand Newton's first law and understand inertia, but discover it on their own, and then also use what they've learned about mass and about acceleration in order to come up with the best plan to push the block the furthest. So they'll have to do multiple trials, multiple different ways that they could try to do it. Is it more weight? Is it less weight? Should they give it more time to run up to it? Should they just set it next to it? What happens if they just set the block on top and then have it drag? How far could it go that way, and get rid of the friction force? And then talk about how you could find the frictional coefficient. I might only do that with the honors kids because that's pretty high level. But there's any number of things that I can go with this, and it is pretty open-ended. And the students can, again, evaluate, they can judge which one is better, they can defend their answers, they can have video evidence about how they can show why theirs was better and why they think it was better. So I'm really excited to get this started. But like a lot of things where I'm kind of nervous trying to work out the kinks and see where the kids might get derailed, I take my after-school kids and I have them practice it because I do math and science tutoring. So this is actually during after school. So I asked him to do a couple trials. So I'll play this. Actually, I can play it now while I'm talking through it. I don't know if you'll be able to hear the video or not, so I might just try to narrate over top of the video. But this is just me and the student trying to kind of work through it. And this really helps me as a teacher, because then when I get to class, I already know where the main things may go wrong or where they may need the most help. Or I might even show a video like this to them so they sort of have an idea. But again, it's not a procedures list where they have to do step by step by step. This is your goal, and this is what I want you to try to do, and this is the different standards that you're trying to learn. And hopefully with the whole competition piece, who can push the block the furthest, they'll have a lot of fun with it while still learning about inertia and really applying what they've learned. And that's what I want them to focus on. So again, just to recap, this is a student-centered activity because the students are coming up with the best way for it to be pushed. They are not, sorry, let me pause this a second. Sorry, I had to pause there for a second. But again, it's student-centered because I don't give them the procedures list and tell them what the outcome is supposed to be. They can come up with their best plan, and they can defend why they think it's the best plan. It would be a little bit more student-centered if I could have them come up with what they want to test about the car, or have them come up with their own learning. That would be even better. Hopefully I'll get there in the future, but for now I'm really focusing on having the students learning and doing, and using what they've learned in the book in order to help them. Or what do you know about inertia? What does the book say about it? How can you reduce friction? And all those things where they can use the information to help them. And then really I'm just going to be the facilitator. I just walk around the room, I help them while they're trying different things, maybe giving them some suggestions or guiding them, redirecting them, but I'm not telling them, first let's do this, everybody does it, second let's do this, everybody does it. I've done labs like that in the past, and it really gets boring for the kids, and it's not discovery learning. Even though it's active and the students are doing labs, it's still not discovery learning the way that I hope that this goes well, and I'll be talking about it more in the discussions throughout the course as well. So again, going back to Bloom's taxonomy, they have to apply what they know about acceleration and about force and about mass, and they're going to have to construct a plan. They'll have to compare one trial to the next trial to see which one's better. And the really good part is going to be the debate. If they debate which is the best way, and they have to be able to intelligently explain what they did and why they did it. They'll have to make conclusions. They'll have to evaluate maybe other groups' methods or their trials. Excuse me. And then maybe once one group comes up with what they think is the best, give the other groups a chance to try that and then compare other groups' strategies with their strategies. And maybe as a whole class we come up with the best strategy, and then we can discuss why it was the best strategy. And throughout the whole thing, we can be hammering home the idea of inertia. The block wants to stay. You have to give it a force in order to get it to move. There's friction that's getting it to stop. How can we accelerate it with the most acceleration and the most force, and really just reinforce all of those different ideas. So I've got about 30 seconds left here before screencast-o-matic. I have a 15-minute block. So independent learning, even when they're working independently, they can do things like an interactive tool such as this. And then when they're working with me directly during labs, it's an open-ended question: what's the best way to push the block, and see what the students can come up with. So I think that's about it. That's about my time, my 15 minutes. And again, this is Andy Reid, Wilkes University.